Hey there. We can think of probability as a measure of belief. But our beliefs change based on evidence, based on our experience. And so does probability. Imagine that you come to the doctor and you ask her, what's the probability that I will get cancer? And the doctor is too busy to look at you and she just says 7%. But you say, well, doctor, but I actually smoke. And the doctor says, oh, then it's 20%. In changing her belief from 7% to 20%, the doctor updated her probability based on the evidence. The mathematical mechanism that allows us to update probabilities based on evidence is called conditional probability. Let's look at this imaginary study on 360 people. Some of them smoke and some don't, and some have cancer and some don't. This is their numbers. Let's first compute the probability that a randomly chosen person has cancer. There are 8 plus 16 people who get cancer. There are a total of 360 people, and this probability is uniform. Any outcome is equally likely. Any person to be chosen is equally likely. So the probability is this ratio, which is about 7%. Let's now compute the probability that someone gets cancer if he or she smokes. In this case, we should only consider the smoker group and completely disregard the non-smoking group. So if you look at the smoker group, there are 8 people who have cancer out of total of 8 plus 32. And that probability is 20%. Compare this to the probability of getting cancer if one does not smoke. In this case, we should only consider the non-smoking group and completely disregard the smoking group. Within this non-smoking group, 16 people have cancer out of a total of 16 plus 304, and that is 5%. This number is 4 times higher than this one. And we can interpret this as saying that smokers are 4 times more likely to get cancer than non-smokers. This is a statement about conditional probability. Conditioned on the fact that a person is a smoker, the probability of getting cancer is 20%. Conditioned on the fact that a person is non-smoker, the probability is 5%. This particular example can inspire us how to define the conditional probability generally. To compute the probability of a cancer if the person smokes, we looked at this ratio, the ratio of people who smoke and have cancer, and means the operation intersection. And we divided this by the number of people who smoke. Here we use the number of these people, but we could equivalently use the probability of a randomly chosen person. And that's because probability is just this ratio. It's 8 divided by the total number of people, and this is the number of smokers divided by the total number of people. 360 would cancel anyway, and we would get the same answer, 0.2. The reason to express this computation in this way is that this now can become the general definition of conditional probability. Instead of cancer and smoking, consider arbitrary events E and F in the sample space. And then we define the conditional probability of E given F as the ratio of P E intersection F, just like here, over P of F, just like here. The meaning of this bar is to indicate that we assume that F occurs, 100% occurs. So this bar stands for logical operation if. And that probability is the probability that E occurs if F occurs. The probability of E given the fact that F occurs. This formula is an important definition. I suggest that you memorize it. Let's look at a couple examples. Consider families with 2 children. If the older child is a girl, what is the probability that both children are girls? Our experiment here is to choose a random family with 2 children. The outcomes possible are that this family has both girls, a girl and a boy and a girl, and boy and the boy. The order here matters because it will be important who is older and who is younger. So let's agree that we put the older first. These are the only possible 4 outcomes in this experiment, and their set, as we know, is called sample space. All outcomes are equally likely. Any combination of any combination of the children's sexes is equally likely. Let's look at these 2 events. The older child is a girl. Let's call this F. And both children are girls. Let's call this E. So F has 2 outcomes, G and GB. G is the first, the older. E, the event that both children are girls, has just 1 outcome, GG. So by definition, the probability that both children are girls, given that the older child is a girl, is this conditional probability that by definition equals this. The probability of F, because all outcomes are equally likely, is a ratio. F has 2 outcomes out of 4, so it's 2/4, and E intersection F has just 1 outcome, GG. So its probability would be 1/4. And the answer is 1/2. This is not surprising, right? The answer to this question, 1/2. But there will be some surprise in the next part. Let's change the condition. Assume that at least 1 child is a girl. What is then the probability that both children are girls? Here, the experiment is the same. We're picking a family with 2 children at random. The sample space is the same. E is the same. Both children are girls. And only F changes. At least 1 child is a girl. That's what we call F. So F consists now of 3 outcomes. At least 1 child is a girl. That's GG, GB, and BG. So the conditional probability, according to the same calculation, is now 1/4 over 3/4. and it equals 1/3. That's a little surprising, right? Another example. Suppose that 75% of all people live at least 70 years, and 63% of people live at least 80 years. Now imagine that you're a doctor, and here comes a 70-year-old person to your office and asks you, what is the probability that I will live at least 10 more years? What would you answer? Do you realize that this problem is about conditional probability? You should. Here we know for a fact that a person who came to you has already lived to 70 years. So this event for the person who comes to you has already occurred. Let's denote this event by F. And the person is interested in living 10 more years, which means living to at least 80. Let's call this event E. The probability of E is 63%. The probability of F is 75%. The unspoken setting here is the experiment in which we're picking a person at random from the entire population. So the probability of E given F, by definition, is this ratio. What is the intersection of E and F? The event E implies the event F. Indeed, if someone lives at least 80 years, then he or she must have lived at least 70. This means that whenever E occurs, F must occur too. The Venn diagram in this case looks like this. So the intersection of E and F, the common part of E of F, is E. That makes this ratio P of E over P of F, which is 0.63 over 0.75, and this is about 84%. That's the answer to that problem. And here's another problem. Assume that on a given day, a person opens the Netflix website with probability 20%. Then, once on Netflix, the person may either rent a movie with probability 15%, or close Netflix website and do something else with the remaining probability of 85%. Question: what is the probability that a person rents a Netflix movie on a given day? There are two events here: open the Netflix website and rent a movie. Let's call open Netflix event F and rents a movie E. What we're interested in is the probability of E intersection F, because you want to rent a Netflix movie. How do we compute the probability of the intersection? Let's look at the definition of conditional probability. If we multiply both sides by P of F, we move P of F to the other side, that will leave the probability of the intersection by itself. So it equals P of F times P of E conditioned on F. P of F is 0.2, and P of E conditioned on F, that is the probability to rent a movie if the person opens Netflix, and that is 0.15. So the answer is 3%. The formula that we discovered in the process is a useful multiplication rule. We will apply it next time. Stay with me.